Hello everyone. Today we'll be learning the difference between RISC and CISC. Okay, RISC full form is Reduced Instruction Set Computer, while CISC refers to Complex Instruction Set Computer. Okay, so what exactly is RISC and CISC? That is what we have to know first. So RISC and CISC refers to two different CPU designs. Okay, two different ways in which we can design CPU. Also, it refers to two different instruction set architectures, because the full focus here is upon the instructions to be executed in the two different designs. Okay, so let's start with the first point. Okay, in case of RISC architecture, number of instructions will be less. What are instructions? These are the operations we want to be executed. For example, add, subtract, multiplication, all those are different kinds of instructions. Okay, so if you consider the list of instructions available in RISC design, it is lesser than the CISC design. Okay, next they are taking the topic of instruction pipelining, and they are saying this has instruction pipelining and this generally doesn't have instruction pipelining feature. So what do you mean by instruction pipelining? So let me just explain the very basic concept of pipelining. If pipelining is not there, this is like, for example, if we consider the case of CISC, what happens? Now when you call something as code, code is nothing but a list of instructions. We have instruction 1, instruction 2, instruction 3. Now these three could be any operation. It could be addition, subtraction, multiplication, load, store, etc. Okay, so what happens here is, now here to make things simpler, we have assumed that all tasks, let's assume fetching, decoding, executing, everything takes only one clock cycle. Okay, so that depends upon the architecture that we are considering also. So for now, let's keep things simple. We'll assume everything occurs in one clock cycle only. Okay, so the very first instruction, if we consider here, what should happen? First, it should be fetched from the memory. Okay, then we have to decode it. Decoding means we have to first understand what is the task to be performed, right? Now here we are dealing with a processing unit which needs to fetch something from the memory, that is bring it from the memory or search from the memory, and then decode it means it should understand what exactly that task is all about. Okay, usually in general in the memory, okay, data is stored in the binary format. Okay, in the sense, if you have some instruction like add, you don't store add in the memory. Let's assume the opcode for that is 0100. Okay, which means that as soon as this particular term or this particular number is seen by your processor, it recognizes it to be addition operation. Similarly, for addition, subtraction, multiplication, there are different numbers specified. Finding what exact task is to be performed is called as decoding. Then you have to execute it. Execute means actually performing that task. If they ask to perform addition, perform that. Okay, and next instruction after that, it is fetched, that is again it is searched from the memory, then it is decoded, then it is executed. Same thing happens for the third instruction. Okay, so this is a case without instruction pipelining. But if you have the concept of instruction pipelining, first step is same. You are fetching the instruction from memory, but while the first instruction is getting decoded, or you try to find out what exact task is to be performed, the second instruction is fetched simultaneously. Okay, so at the same clock cycle, multiple tasks are happening. If you see the third case, the first instruction, okay, they have understood what task is to be performed, so it is executed. So second instruction is getting currently decoded, and third instruction is getting fetched. The thing is, there are different components performing each of the tasks. There is a separate circuit to perform fetching, separate component to perform decode operation, separate component to perform execute. So when that is possible, and when the instructions are simpler, it is easy that simultaneously you perform multiple tasks. Okay, so what will happen if you do this is nothing but in the third clock cycle only you will start getting the output, because execution happens here, and here see you will start getting the output of the second instruction and third instruction. So in every clock cycle you will start getting the output. Okay, so that is some basics about instruction pipelining. So that feature is there in RISC, but it's not there in CISC. Next is about orthogonal instruction set. Okay, so for that first you should know there are something called registers. Okay, and there is something called addressing modes in CPU. Okay, CPU or the processing unit that we are considering has registers. Registers are memory elements. Okay, and if we speak about the speed, they are among the fastest processing memory units. Okay, in general we consider cache as the fast memory units, but if we consider processors, if any data is stored in registers, okay, and any operation is performed on it, so it will be executed very fast. Okay, fine. And when you say addressing modes, they are the different states in which CPU can work. Okay, they have supervisor mode and so on. There are a lot of modes there. Okay, but when you say orthogonal instruction set, these instructions which are available in a RISC based system, okay, it allows the same. If you have one particular instruction, let's assume addition, okay, that can be performed on any registers and in any mode. Okay, if you consider based on what processor we are speaking about, okay, there will be n number of registers. Okay, and what they are saying is on all the registers you can apply these instructions. Okay, while the CISC, it's non-orthogonal, you can't perform one particular instruction to all the cases, all the modes and all the registers. Okay, it depends upon the instruction which can be applied, which one cannot be applied. Okay, operations are performed on registers only. The only memory operation are load and store. Registers are one type of memory elements. Okay, these are the fastest processing units, but there are slower main memory. You want to bring the data from main memory into this smaller memory elements called registers, or you want to store the result into the memory or the main memory. In that case, load and store instructions are used. Any other operations cannot be performed on main memory, but that limitation is not there in CISC. Okay, number of registers available is more here, and number of registers available will be less here. Okay, and the instructions here are simpler. Here it is more complex. What task you will be performing by, let's assume you have 4-5 instructions here to perform one task. Same thing can be carried out by one single complex instructions there. Okay, single fixed length instruction. I think while explaining about instruction pipelining, I told something about these processors won't understand English or any other language. It only understands binary value. Okay, so the entire instruction, so when I say entire instruction, now that instruction could be add, let's assume, okay, R1 comma R2 comma R3. What happens here is add R3 and R2 and store the result in R1. Okay, if I have some instruction like this, that will be actually stored in the memory in the form of binary values. Let's assume 32 such numbers are there, then that becomes a 32-bit instruction. Okay, so this instruction will be stored in the form of a 32-bit binary value in the memory. Okay, so what they are saying is, while storing such data, all instructions have fixed length, in the sense if one instruction is 32-bit, all instructions are 32-bit, while this is variable length, which means if let's assume one is 32-bit, one more may not be 32-bit, it might have some other length of the data. Okay, and if you're considering the physical aspect, the silicon usage and the pin count is less here, it is more here because it is more complex instructions are there, so decoder logics and all are required, which uses more silicon. Okay, and this uses Harvard architecture. This could be Harvard or von Neumann. If you say Harvard, means there will be separate data and program memory. Here it has same memory. Okay.